all right? Wanted to come here because of that big black, well, it was like a spot in the middle of the board, you know what I'm talking about? And it was like delaminated and there's nothing I could do about it. So I asked them to move, and this is what they gave me. So it's a little bit smaller classroom, but it'll work. Y'all doing okay? Yeah? All right, let's get going. We have a lot to do today. So I'm gonna be working, I think, at a little bit faster pace because last time we were supposed to cover 10-2 and we didn't, but we were really kind of taking our time. It was the first day, and I wanted to give you a false impression that things were gonna be great. Okay, vectors. So just show of hands real quick. How many of you have done something with vectors? Okay, some physics or something like that? Okay, just kind of want to see. I'm going to act like you haven't seen a vector ever, all right? All right, so what are vectors? Vectors are objects that have two main properties. They have what we call a magnitude, and they have a direction. And the magnitude is also called the length or the norm of a vector, and then the direction in which it points is the other characteristic that we need in order to define a vector. So it's a very general definition. A vector is a very general thing. Now you may be familiar with vectors as being these arrows, right? Something like that. And in two-dimensional space, a vector is going to look like an arrow. It's basically can be anywhere we want in two-dimensional space, pointed in any direction, and it can have different lengths. So that vector has a length, right? I can make it longer, change which way it points. Pretty simple looking thing, right? So we won't want to overcomplicate this. Now in three-dimensional space, we can still have a vector, but now that we have these octants, we would be concerned about, you know, where this thing is. So it's kind of hard to see, but y'all get it? You'll see where that is? All right, so there's a three-dimensional vector. Now some language when it comes to vectors. Where's the language? There we go, sorry. All right, so when we have a vector, first, the way we notate it is we have to call it something. So the normal letter we use for a vector is V, but you'll also see U, W, those are the three standard letters we use to represent a vector. But you'll also see that we put this, it's like a half arrow on top of it. It's like we took an arrow like this and then we cut the bottom of it off. And that's the notation we use to denote a vector. And you will also see in most textbooks a vector, they won't use that arrow. Instead, they'll make it a bold. So it'll be a bold letter instead of a non-bolded letter. Now, when I'm on the board, it's obviously hard for me to do bold letters, so I'm going to use this notation instead of bold. Understand? So that little symbol lets us know we're talking about a vector, as opposed to if I just write V, then V could be like X. And normally we reserve things like X, Y, Z. We reserve those letters without this. These are just like variables that represent real numbers. So you know, X is 2, and it's a number, right? Where here, if I use V, then V must be a vector. Now we also have some language. We call this a displacement vector. This part of the arrow is the initial point, or called the tail of the vector, and then the tip of the arrow there is called the terminal point, and of course that's the tip. So you'll hear me say tail to tip or tip to tail. This is the tail, that's the tip, all right? So all vectors will have that, unless it's the zero vector, but we'll get onto that later. Make sure I covered everything there, yeah. All right, equivalent vectors. Two vectors are said to be equivalent or equal if they have the same magnitude and same direction. And the thing to note here is that the position does not matter. So if I have a vector, there's a vector, right? Then if I take that vector and just slide it to the left, these two vectors are equivalent. So the fact that they are not laying right on top of one another doesn't matter. As long as they're pointed in the same direction and they have the same length, then they are equivalent. And that's an important aspect of vectors that you do not get with lines. Like if these were lines, or if these were just like line segments that started and ended at a point, then these two line segments would not be equivalent. But as vectors, they're equivalent because there's only two things we need: length and direction. That's it. And that's important because when we use vectors like in physics, vectors usually are used to represent force. So if I'm grabbing this chair and I'm pulling it across the room, then we can represent the force I'm applying on this as almost like my arm. So I have a direction in which I'm pulling, right? And then how hard I'm pulling can be represented by how long the vector is. But see, as I move through the room, we don't want that vector to change. We want it to still be the same thing, right? So as I move across the room, the vector's not changing. So its position doesn't matter. It's just the angle and the length of it. Does that make sense? Okay. All right, now, how do we determine a vector from points? So let's say somebody gives us 2 points, all right? In two-dimensional space, we have 2 points, and we would like to somehow represent the vector that goes from A to B. So that would be the vector from A, the point A to point B. And notice this notation right here. A comes before B, right? And then that little half arrow thing. That would be a way that we could represent the vector going from point A to point B. Now, if I do the vector that goes the other way, from B to A, are those two vectors equivalent? Are these two equivalent, question mark? I heard no. Why not?
Opposite direction.
Opposite direction. They have the same length, but they're pointed in opposite directions. So they are not equivalent. So how do we actually come up with the vector? Well, now it's time for some new notation. So this is going to be, I guess what I could do is, let me label these points. This point right here, B, is the point, what does that look like, 2, 3? And then this vector right here looks like this point right here looks like it's the point -1, -2. Would you all agree with that? Does that look about right to you? Like as a point 2, 3, and then this point is -1, -2? Yeah, -1, -2. So if I wanted to somehow write the vector that goes from A to B, then the way we do it is as follows. So here's where the notation starts to become new if you've never seen vectors. We use these things called angled brackets. Okay, it's not a parenthesis, it's not a bracket, it's an angled bracket, that's what it is. And then what we do is if we're going from, I should switch those. If I'm going from A to B, then what we're going to do is we're going to take the x-coordinate of where we're ending, right? We're going from A to B. So we're going to take that x-coordinate and we're going to subtract this x-coordinate. So I'm going to take 2 and subtract -1. And then to get the next piece, I take the y-coordinate and subtract this y-coordinate. So 3 minus -2, close the angle bracket. And then I get 2 numbers there, right? And what would they be? This would be 3 and then 5. So the vector that goes from A to B can be represented using this notation as the vector 3, 5. Now look, there's a big difference between this and this. If I ask you to plot this point, this is a point, right? How do you know it's a point? Because I'm using parentheses, right? If I ask you to plot that point, you go out 3, you go up 5, right? And you would put me a point right there? That is not the same as the vector 3, 5. The vector 3, 5 is this object that has a length and a direction. And if you were to start at the origin, right here, and draw an arrow that would go up to that point up there, you will find that this arrow that I drew, this vector, is equivalent to the green vector because they have the same length and they have the same direction, even though they're not right on top of one another, right? Okay. So you're going to subtract, the notes say here that if you're going to go from the point A, which we'll call x1, y1, which would have been these, to the point B, which is x2, y2, which was the 2, 3, then you're going to take the x2, subtract the x1, and then the y2, subtract the y1. The order is important. So how about if we go the other way around? What if we go vector from B to A? Then where do we start at? We're going to go -1. So we're ending here, right? So we start here, -1, take away 2. And then -2, take away 3. And we're going to wind up getting -3, -5. And do you notice something about that compared to the other one we just got? Same, just different signs, right? And it turns out that that's how you can flip a vector over, is just change the signs. And that'll point it in the opposite direction but still have the same length. And we'll get to that later. Pretty straightforward here? Okay. Now, in three-dimensional space, we are going to be going from a point in three-dimensional space. Now it's going to have 3 coordinates, right? 3 coordinates. It's going to have x1, y1, now z1 because we're in R3. And then it's going to go to a point B, which is x2, y2, z2. So if you want to notate the vector from A to B, here's the notation. Angle bracket, subtract the x coordinates, subtract the y coordinates, subtract the z coordinates. Again, always starting with where you're going to. So if you're going to B, you're going to start with x2, subtract x1. Now if we flip over and go from B to A, these things flip. Again, is that pretty straightforward? Do I need to go through an example of that? We're good? Okay. So yeah, here's an example. Let's just do one of these. We'll just do one. Oh. Who was not here last time? Just you? Could you put your name? Just put your name in this marker on that stick for me. All right, Adam, where's Adam? Adam Reed. Adam, okay, you're up. So I'm going to let you choose, Adam. Do you want to do part A or part B?
Part A.
Part A? Okay. And for part A, I'm just going to ask you to tell me what to write down. Don't give me the final answer. What I want is, like, just you tell me all the notation that I need to write for part A. And I'll start with this. Okay, so equals, now what?
It's -2 minus 6.
-2 minus 6. So angle bracket, right? Angle bracket. And then you can go -2, subtract 6. Good.
8, subtract -5.
Good. And comma, right? And then
10 minus 6.
10 minus 6. Close out the angle bracket. There we go. That okay, everyone? Because we're going to B, from A to B, we start with these guys and subtract those guys. All right. So that'll just give you a final vector. Let's see. -8, 13, 4. There we go. So that is the vector that goes from A to B. Now, in three-dimensional space, if you wanted to see where this was, like what it looked like, you would actually have to do that. Now, you don't need to do it right now, but I'll just show you real quick how this would work. I would go to the point, -8, 13, 4, and I would draw an arrow from the origin to this point. So -8 would be, let's see, if this is x and this is y and this is z, then I go -8 on the x would be 1, 2, 3, 4, 5, 6, 7, 8. And then 13 on the y would be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. and then I'd go up 4, so like up 1, 2, 3, 4, somewhere around there. There's my point. If I draw from the origin to that point, that would be the vector AB, right?
So we're going to go from the origin to the point.
Yes. Now remember, that could be moved around, okay? But if you're trying to visualize this vector, then you can always start from the origin to that point, and that vector would be equivalent to this vector, right? And just imagine now moving it around. So you got this vector. We're just not allowed to change its length, but we can move it, up, down, left, right, just as long as we don't do that or stretch it, okay? All right, we good? All right, so this is just arithmetic in some new notation. That's all it is right now, right? All right, the zero vector. Now the zero vector is somewhat interesting because it is a vector, but it lacks something. What does it lack? Well, I mean, you could argue its magnitude. Direction.
But it has a 0 degree, right?
Well, does it? And what would the length of this vector be? I mean, think about it, right? Like, how long is this vector? 0, right? Because this vector 0, 0, if I were to draw it, I just told you you would go to the point 0, 0. In two-dimensional space, you would go to the point 0, 0, and then you would draw a line from 0, 0 to 0, 0, which means you would just draw a point. And a point has no length. So this thing doesn't have a length to it, does it? Nor does it have a direction, because which way is a point pointed? It's not really, right? So the zero vector is kind of the exception. And a lot of times in this section, we'll be talking about properties of vectors, and we'll always want to say, if the vector is a non-zero vector, then this is true. Because if it's a zero vector, the properties kind of fall apart. Does that make sense? Kind of, yeah? All right. Now, keep in mind, there is a huge difference between these two, right? These are not the same thing. This is the number 0, and this is the zero vector. The zero vector has, either in two-dimensional space, the zero vector has angle brackets with 2 zeros. In three-dimensional space, angle brackets with 3 zeros. That is not the same as the number 0. Are y'all okay with that? Okay. Now, some more language. When you write a vector down in two-dimensional space, if you have a vector, it's going to have 2 numbers in there, right? Could be 0, 0, but could be 2, -5. These two numbers are called the components of the vector. As opposed to when when we do a point, like if I say, hey, go to the point 3, 5, we could graph that point. These are called the coordinates of the point. When you have a vector, we don't call them coordinates, we call them components. So this V1 would be what we call the x component, and V2 is what we call the y component of the vector. And if you move into three-dimensional space, you've got 3 numbers in here now, V1, V2, V3, and they're called the x, y, and z components respectively. Again, this all straightforward still? And y'all remember that these notes are online, so you don't have to make sure that you're copying everything down. I wouldn't expect you to have to do that, right? All right, moving along. Our first little rule when it comes to vectors. And I don't think I stated on here, I didn't, I should have. When we are trying to add 2 vectors together, we have something called the Parallelogram Law, and this only works when you're working with non-zero vectors. So if I have 2 vectors that are both non-zero, and I add them together, geometrically we have something kind of cool happen. So let's say I have 2 vectors. I have the vector v, which has this length and points in that direction, the vector u, which has this length and points in that direction. If I try to add them, then here's what I'm going to do. Remember, vectors can move around, right? And they're still the same. So I'm going to move I'm going to move u here to the left. Still the same vector, isn't it? I have not changed it. It's still pointing the same direction, same length. I'm going to slide it up now, and when I add them, there we go. So do you see this new vector that I just had the computer draw? It's almost like if you started from here at the tail of V. If I started at the tail of V and followed the path to the tip of V, and then I connected the U vector, the tail of U to the tip of V, understanding that language? Tail of U to the tip of V, followed that path, I would wind up right here, right? So after first following V and then going U, I wind up here. So at the end of the day, V plus U gives me this vector, which goes from this point to this point. It's like the net result of both of these vectors is that one. Understand? Now, I could also, you know what, I'm going to do this in purple. I'm going to draw this vector up here and just leave it here. This vector right here was the vector V, plus U, like that. Now instead of doing that, I'm going to move this back to where it was. I think it was somewhere around here when I started. Instead of taking the tail of U and attaching it to the tip of V, I'm going to take the tail of V and attach it to the tip of U. Okay? So see if we can do this. I'm going to try, first I'm going to try and move things around here. Go, yeah, move that over, move that down. There we go. You see that? See that? Yes? Okay, do you notice that this vector is the same as this vector? They have the same length and they point in the same direction, don't they? So now, just to make it a little easier to see this, I'm going to move some things around. Move the red one over 2. I'm going to move the blue one over 2, and then I'm going to move the red one the red one up 2, and then I'm going to move the blue one up 2, like that. Okay. So that's the same vector, right? I'm going U, so I'm starting here. I go through U, and then I go through V, and I wind up here. So at the end of the day, I went from here to here. If I move U back over to the left, how we got that purple one? Remember, that's how we got the purple one, right? Then if I put all these together, I have to draw these and leave them. I'm going to move U back. Come here. There we go. That picture right there is what we call the parallelogram law. So that is a parallelogram, all right? It's just saying that when you add two vectors together, U plus V is the same as V plus U. It doesn't matter which way you order them, you're going to get the same result. And if you sketch them all, you wind up getting a parallelogram, right? So I put here, when we add two vectors together in R2 or R3, we take the tail of one vector and paste it to the tip of the other, right? Tail to tip or tip to tail, however you want to say that. All right, so now on this one, this is going to be an interactive one. And it's going to take somebody who's willing to get up here and be brave. So I'll ask first I'll ask for a volunteer. If anyone would like to come up here and show us the vector V plus U. Any volunteers? Yes? What was your name, sir?
Milton.
Milton? Yes. You're going to be on camera, is that all right?
Absolutely.
Oh, you're okay with that? All right. So go ahead. I just want you to grab whatever you need, marker, do your best to show me V plus U. Or show us V plus U. And feel free to think out loud.
All right, here.
Okay?
It's already at the origin.
Okay?
And then I'm going to move this one all the way up to here.
That one's W.
Oh.
Yeah, grab
Oh,
V, yeah.
But isn't this the resultant?
It could be at the end, but these are just 3 arbitrary vectors right now.
Okay.
Yeah.
All right, so then this one goes up here.
Okay? And just do your best. You don't have to make it perfect. Okay? Could you label that for us? That vector is V. Okay, so
And this would be the resultant.
okay, which we will, yes, that's good enough. Very good. So you're using some language I haven't used yet, but we may as well talk about it. So all Milton did was he took V and he attached it to U, because this says we want to attach the two together, right? Add the two. So we go tail to tip or tip to tail. So you took the tail of V and wanted to attach it to the tip of U. So you took it up, right? Took it over, and that's your V. Then what you call the resultant vector is the result. Sorry, thought that was black. Right here. That black vector is the resultant vector. It's what we could call it, but this is what it is. It's V plus U. Or if you'd like, you can switch the order. It doesn't matter. All right? Okay. Do y'all follow that? We don't need to do any more examples of this? Okay. All right, so that's how you add. I was showing you how we can add up vectors geometrically, visually, but how do you do it arithmetically? Like if somebody gives you 2 vectors, right? If they give you a vector U in 2-dimensional space where it has 2 components, U1 and U2, you have another vector V which has 2 components, V1 and V2. When we add them, look how simple it is to add them. You just add the components up, and you get a new vector. Super easy to add up vectors. And subtracting is the same way. If you subtract 2 vectors, you subtract the components, but just make sure with subtraction, order does matter. Okay, so U minus V, you do the U1 minus V1, U2 minus V2. We're going to do an example of this in a second. In 3-dimensional space, it's the same thing. You have 3 components, you just add up each of the components or subtract the components, and that is vector addition and subtraction. Thought I had an example. There's an example coming. All right, so now if somebody gives us a vector, we are allowed to multiply that vector by a number. And this is by a, what did I just say? If we have a vector, we are allowed to multiply it by a what? A number. And that's called scalar multiplication. The number that we're multiplying it by is called the scalar. So let's say we start with the vector V and we multiply it by C. Then that C, that number in front that we put in front, has an effect on the vector. It does something to it. If the absolute value of C is bigger than 1, it's going to stretch the vector out and make it longer. If the absolute value of C is between 0 and 1, it's going to shrink the vector and make it smaller. If C is negative, it's going to flip the vector over and point it in the opposite direction. And the way you can do it mechanically is if you're given a vector V and then someone says, hey, multiply the vector times C, then all you do is you just multiply each component by C. So it's almost like you're distributing that scalar into the vector. And then everything that we just talked about right there can be extended into 3-dimensional space. All right, very important definition here. Parallel vectors. Any 2 non-zero, I forgot to put it in there, any 2 non-zero vectors are said to be parallel if they are scalar multiples of one another. Note, they could be pointed in opposite directions. Let me give you a quick example of this. Are those 2 vectors parallel? Let's draw it first. The vector 4, 2, I could draw by going out 4, negative 2, going down negative 2. I could draw a point, right? And then I could draw a vector from the origin to that, right? And that would be that one. Agreed? Then this vector, negative 2, 1, would be to the left 2 and up 1. And I draw a vector from the origin to that one. And that would be this vector. Are they parallel?
Yeah.
Yes. They're parallel because they are scalar multiples of one another. Now, how can I tell that they're scalar multiples of one another? I mean, visually, they look like they have the same direction, don't they? Except they're opposite? Yes? So, with this one, how could you turn this one into that one? What would you have to multiply it by in order to turn that to that? Negative 1/2. So if I take negative 1/2 and multiply it times 4 negative 2, then the result would be, distributing this through, would be the vector negative 2, 1, which is that vector. So there was some number, right? There was some number that when we multiplied this vector by that number, we got back this vector, right? Now you could have looked at it the other way around. Is there a number you multiply this by to get that? So go this way. Negative 2, right? Multiply that by negative 2 and you're back here. So they're scalar multiples of one another, aren't they? Let me see. I think I missed the... Yeah, this thing. I should have shown you this first. Sorry. This is a visual that shows you the effect of having C being multiplied on your vector. So we have a vector V, which is the vector 3, 3. Sorry, I'm not using angle brackets here. That's the vector 3, 3, which is out 3, up 3. And then I'm about to multiply it by a number. And right now I'm multiplying it by 1. So what happens if I make C 2? If I change this C to 2? It should go twice as long, right? There's 2V. So there's V. There's twice. So it's twice the length, right? And if I multiply it times 1/2, it's going to shrink that vector. Okay, so there's your half V and there's V. But if I go negative, now, multiplying by negative 1, I have the same length vector, but now I'm pointing in the opposite direction. Make sense? Okay. Next thing, magnitude, or the length of a vector. So if somebody gives you a vector, and they want to know how long it is. If you actually wanted to know, if you got a measuring tape and like measured the length of the vector, to get the length, first of all, we denote it using the absolute value symbols, like the absolute value symbol that we've used in the past. And you put that around the vector, and this is the computation for it. And does that computation look pretty familiar, like straightforward? It's almost like your a squared plus b squared equals c squared, which is exactly the way you would get it. And this will give you how long the vector is. And in three-dimensional space, with a vector with 3 components, your formula, again, is very similar to the distance formula we had for points from last class. We're going to get to practice here. Lots of notes right now. All right, here we go. Let's go to example 4. Let's see how fast we can go through this. Paul? Where's Paul? 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 You're Paul? Carrillo? Is that right? Okay. All right, Paul. Give you a second to look at this. I want you to just do part A for us. So I'll start us out by this is going to be the answer. It's going to be a vector, right? So can you tell me what the actual computation I'm going to do inside is?
You're mostly going to subtract the components of
Yes. Okay, so I would start with doing what minus what here?
You do 2 minus -5.
2 minus -5. Everyone on board with that? Okay, and then comma,
3 minus 7.
3 minus 7, comma,
And then -5
subtracted by -2, and then close that out, and then let's just finish this up. This is 7, -4, -3, yeah. Okay, so that is the vector v minus u. Good. Ricky, where's Ricky? Ricky, without doing any work, without actually doing any numbers, do you have an idea of how we could find u minus v?
Flip the signs.
Flip the signs, very good. Now, look at what Ricky's doing here. We're trying to find u minus v, right? We're trying to find that? But isn't that the same as taking v minus u, whatever that vector is, and doing a scalar multiplication of -1? So this is a vector, right? So if I do a scalar multiplication of -1, I distribute here and here, then I'm going to get that, right? So all I have to do is take that answer and change all the signs. So -7, 4, and 3. Good. Christopher. All right. Christopher, if you could look at part C. Unfortunately, we can't use any of that. So for part C, we're going to have 4 times v. So v, I'm just going to write down the vector, right? 2, 3, -5. And then we're going to subtract from that 3 times the vector u, which is -5, 7, -2. Right? So, Christopher, this times this is, we call this what? Scalar multiplication, right? So we have scalar multiplication, and what would this be, this first vector, Christopher?
8,
8,
12,
12,
and -20.
-20, and then we're going to, how do you want me to do this? Do you want me to leave it as a minus, or do you want to distribute it through as a -3? It's kind of your call here.
I guess we could just keep it a minus.
Keep it a minus, so this is going to be minus, and then you're going to pass a 3 through, right? Okay, so that's a new vector,
It's -15.
-15,
Was it 21?
21.
And, -21.
No, yeah, because we kept the negative, yeah, so that's why I want us doing this.
Yes.
Yeah, okay, then
And,
-6. Okay, so you just have to be careful with the signs there, right? If you're going to keep the negative here, then you're passing the positive through. And now you have to put those two together, which will be, let's see, new vector. You want to keep going?
Yeah, is that 23?
Yeah, so this minus, why don't we do this right now? Let's get rid of this minus. Well, see, there's like 2 different ways to do this. Let me do it this way. I'm doing 8 minus -15, right?
Yeah.
Okay, and the next one, 12 minus 21. Right?
Wait, shouldn't it be the other way around since it's v and u? Like v first, then u?
V first, then u.
V minus.
This is v, right?
Yeah.
And this is u, right? This is 4v minus 4u. And then this is just 2 vectors being subtracted. So I'm just going to go this minus that, this minus that, this minus that.
How come on the other ones it was like flipped, like you did the second vector first? Like,
Did I?
I think he's talking about finding a vector for points.
Yeah, from A to B, you
Yeah.
need to try B first. Or B
Yeah, you might be thinking if I give you 2 points, not vectors, but if I give you 2 points, right?
Right.
Then it matters which one you're going from to the other.
yeah.
All right, I can continue? Yes. Okay, so -20 take away -6. -20 take away -6. And at the end of the day here we get, Christopher, you're off the hook. 23, -9, -14. All right, there we go. So that's just practicing with some arithmetic, right? Sorry, Audrey. Where are you? There you are. You got next, Audrey.
So would I put that in absolute value?
Yeah, so we want the magnitude of this vector. We just got that answer. Here it is, right? So for this part D, what we want to do is take the absolute value or the magnitude, okay? It's not technically the absolute value anymore because we're dealing with vectors. We want the magnitude of that vector. And the formula for that is to take the square root of the sum of the components squared. So you have to square each one of those and then add them all together. So I'm going to need someone with a calculator here. 23 squared plus negative 9 squared plus negative 14 squared. And that's just the formula from the previous note, right? I had that on the board a second ago.
It's 28.39.
28.39?
Or the square root of 806.
806? Okay, so we'll leave it as an exact answer. We'll just leave it like this. You can give me the decimal, but I would like to see the exact first. So if you actually want to get on your calculator and take the square root of that, great, but I do want this result. And you don't need to do anything with it. Like if this breaks down, who cares? Let's just leave it as root 806. All right, that's all arithmetic. All right, unit vectors. A unit vector. Any vector that has a length of one unit is called a unit vector. So you can almost imagine that in two-dimensional space, imagine the unit circle. Any vector that would go from the origin to the edge of the unit circle would be a unit vector, wouldn't it? But also, if I give you a vector, that blue vector, no matter what that blue vector is, unless it's the zero vector, as long as it's not zero, no matter how long that blue vector is and no matter what direction it points in, there's always a vector that points in the same direction and has a unit length. Do you agree? You give me some blue vector, I will always be able to find a vector that points in the same direction but has a length of 1. Now you might argue, well, what if you make it shorter than that? Well, that vector down there still has a direction, doesn't it? The blue one? And there still is a vector that points in the same direction, just with a length of 1. So if someone gives you a vector and asks you to find the unit vector that points in the same direction, how can we do it? Does my question make sense? Let's say somebody gives us a vector, v. I'm just making this up. 3, negative 5. How can I find the vector that would point in the same direction as that, but have a length of 1? So just think about it. You have to shrink it, don't you? Yes.
You could find the magnitude of v.
Okay.
Given that, use the reciprocal of that magnitude as a scalar multiple of v.
Okay, so that is correct. Why does that work?
Because any number multiplied by its reciprocal is 1.
Okay.
So multiplying the vector v by the reciprocal of its magnitude changes its magnitude to 1.
Okay. Yes. And let me try and word that, I guess. I'm hoping everyone follows that. But this vector has a length, right? It has some length. Let's just say, the length of that is magnitude of v. Agreed? So if I take 1 over the magnitude of v, and 1 over the magnitude of v is a scalar, because the magnitude of v is a number, right? That's how long it is. 1 over that is still a number. If I take this vector and I multiply it by 1 over its length, I will shrink it, won't I? I will shrink it by a factor of its own length. And that means whatever its length was now becomes 1 divided by its own length, which means it would have to be 1. So that is basically the formula for it. And that's the next note. So given any vector, u, I'm using u here, in 2 or 3 dimensional space, we can find a unit vector pointed in the same direction as u by computing the following. So here's what we just said, right? We said you take the vector u, scalar multiplication, this over this, that's 1 over its length, and then times the u, distribute through, and you should get a unit vector pointed in the same direction. This is just different notation. If you do u, the vector u divided by the length of u, that is just the same way it's just another way of writing this. Imagine you're just sliding that underneath, right? So let's do an example. Find a unit vector which points in the same direction as this one. So what would be our first step? Find the length of it, right? So I just quickly find the length. The length of v is the square root of 4 plus 9 plus 25. So I just real quick in my head squared each of the components. And that's going to be root, what is it? 38. Okay, that's the length of v. Now what I need to do is take 1 over that length and multiply the vector v by that length. And so now, because it's a scalar multiplication, just distributes through to each component. So this becomes it's still a vector, right? It's 2 over root 38, comma, 3 over root 38, comma, negative 5 over root 38. That's your answer. That vector should be pointed in the same direction as that one, but its length should be 1. How could we check to see if that's a unit vector?
Square them all, add them.
Yeah, square them all and add them, right? So what would happen if I asked you for the length of this? We should get 1, shouldn't we? Okay, so square that. What do you get? 4 over 38. Add to that this one squared. That one squared. And then put it all under a square root. And if you do that, you get 38 over 38. It's 1, square root of 1, 1. So the length of that is 1. So that just verifies that it did give us a unit vector. How do we know it's pointed in the same direction? We scaled it, right? When you scale a vector, it's going to stretch it or shrink it. It could flip it over, but it didn't get flipped over. Why? Because that's positive, right? So we know it's pointed in the same direction. It's just got a length of 1 now. All right, standard basis vectors. Has anyone taken linear algebra? Taking it right now? Who said that? Okay, so in linear algebra you'll learn a little bit more about this, but there's some important vectors in 2- and 3-dimensional space respectively, and they are what we call the I hat, like put on a hat, I hat and J hat vectors. That's in 2-dimensional space. I hat is the vector 1, 0. And if you look at that vector, starting at the origin, it goes out 1 unit, right? There it is. That's I hat. J hat points straight up, 1 unit. So that's J hat, and this is I hat. The reason they're so important to us, and the reason we call them the standard basis vectors in 2-dimensional space, is that, first, they're both unit vectors. You can see that they're unit vectors just by looking at them when you draw them, right? Is it obvious that they each have a length of 1? So they're both unit vectors. Also, every vector in R2 can be written as a linear combination of those 2 vectors. Let me explain. take any vector you want in two-dimensional space. Any vector you want. Here you go, except for the 0 vector. Take any vector you want. I can draw that vector by just using some combination of I hat and j hat. You can see here, to draw this vector u, I could do this red one and that red one together, tail to tip, couldn't I? Like I could just take this one, move it over, and you would have that, right? Now, to get this red one down here, the red one down here is pointed in the same direction as I hat, isn't it? So this red one is a scalar multiple of I. Now I'd have to multiply it by 2.436 or something like that to get it to here. But it's just some number times I, scalar multiple times I, plus, that's this vector here, which is some scalar multiple times j. Some scalar multiple times j. Make sense? That will work for any vector you want. Doesn't matter where you put them, you're going to be able to somehow scale I and j and then add them together to get any vector in there. So what we call this in linear algebra is we call this a basis for R2. And this is what we call the standard basis. There's another property of these two vectors that I don't state here that they'll state in linear algebra, is that this is what we refer to as an orthonormal basis, which means that not only are these two vectors unit length and they span the entire space, they are orthogonal. They are perpendicular to one another. Because you can still have basis vectors that don't have to be perpendicular. But because these are perpendicular, it's like the ultimate basis, standard basis. All right, I'm kind of getting outside of what we need to talk about. I don't use I hat and j hat that much in here. I know in physics you use it all the time, but in here I don't. I just use 1, 0, and 0, 1, okay? Because that's what they are. They're just two vectors. Now, in three-dimensional space, you have, of course, a third vector you need to have a basis. So you have the I hat vector now becomes 1, 0, 0, because three-dimensional space. The j hat vector becomes 0, 1, 0, and k hat becomes 0, 0, 1. So now you have three vectors that all have unit length, and they are orthogonal also, even though I don't state it here. But you can get to any vector in three-dimensional space using these three vectors. This is the last example. So in this, we just want to practice writing things out. So watch what I'm going to do with this vector. I'm going to take this vector and I'm going to try and use it using I, j, and k. I hat, j hat, k hat. All right? So the way I want you to see this is first realize that v can be rewritten as 2, 0, 0, plus 0, 3, 0, and then plus the vector 0, 0, negative 5. Do you all agree that that's v? It's those three vectors added up together? And then now, realize that this first vector, I could pull the 2 out. Right? I could take the 2 out. Here I could take the 3 out. And here I could pull out the negative 5, couldn't I? I'm going to make that minus. And change all those to 1s. And now this is, by definition, I hat, j hat, k hat. And so now you have 2 I hat plus 3 j hat minus 5 k hat. So in physics, you might see this, but that's just that vector. That's all it is, right? It's just that vector right there. The thing is, in physics, there's a lot of cool properties that when you do a dot product of I and j, you know that it's 0 and things like that. So it's nice to use I and j in physics. Questions, comments, concerns? Can we move on, or
You need the brackets for that last one?
did I brackets for?
Do you need the brackets? Back, J, very bottom.
Do I need brackets? What do you mean brackets? The angle brackets around k and j and I? Do not need them.
No.
Nope. The definition of I hat is the vector 1, 0, 0. So when you write j hat like that, it's understood that it is a vector. It's that little symbol, that little hat there, that lets you know we're talking about a vector. And it's bolded, I think, in most books too. All right, that's it for 10.2. We're moving on to 10.3. If you're wondering, like, is this ever going to get interesting, like harder or anything? I mean, it will. We're just getting the preliminaries out of the way here. Okay. We have seen that if somebody gives us two vectors, we can add them and subtract them, right? You get the parallelogram law. We also know that you can take a vector and multiply it by a number, right? And that scales it. That either stretches it, shrinks it, or flips it over. But what if I get two vectors and I ask you to multiply the two vectors together? Multiply them. Can we do it? Yes, right? But it turns out that with vectors, it's very special because there's actually two types of ways we can multiply vectors together. There's two ways you can do it. You have what's called the dot product, and then the next section is called the cross product. And they give you completely different answers, which is very strange because if I ask you to multiply 4 times 8, right? You don't sit there and go, which multiplication are you talking about, right? I mean, we all know multiplication we're talking about. But if I give you two vectors and I say multiply them, you have to clarify whether or not you're talking about the dot product or the cross product. And that's all going to be in the notation we use. That's how you know which is which. So the dot product is super clean, super easy to compute a dot product. Okay, so let's say you're given two vectors, v and u, in two-dimensional space. So v1 to v2, u1, u2. If you want to find the dot product, then here's the notation we use. We use u with a dot. That's like, usually in a textbook, it's like a bold dot. As opposed to, you know, we've used dots in the past. Like, we say like 4 times 3 and we put a dot there. This dot is usually like big and heavy. And that way you know it, you know, it's different from the regular multiplication. All right, so you take a vector u, you dot it with v, and look at the computation. What do? You take the first component here times the first component here plus the second component here times the second component here. So v1 u1 plus v2 u2. And that answer is going to give you a what? What's that answer going to give you? A number. A number. That should be very strange to you because this is probably the first time in math that this has ever happened. Like, think about it. When you were a kid and you were asked to multiply numbers, right? You always took two numbers, put them together, multiplied them, and you got a number, right? In college algebra, you were asked to take two functions, right? And multiply them together, and what did you get? After you multiply two functions, you get a new function, right? Yes? You take two dogs, let them hang out for a while, you're going to have little doggies, right? Rabbits, you can have rabbits. Two vectors, dot product, number. Not vector anymore, right? It's strange. And your first question should be, what does the number represent, right? Like, what is it? So the dot product is the sum of the products of the components. It's vital for you to notice dot product yields a number, not a vector. Also notice the bolded dot, blah, blah, blah. Now, in three-dimensional space, I'm going to answer what it is, okay? But in three-dimensional space, everything runs just the same. Except now you have this one additional multiplication to do at the end. So you multiply the first ones together, add, second ones together, add, third ones together, add. And again, your result is a number. All right. Let's just let